Good morning, students. So in last class we are discussing about crystal field theory. So already crystal field theory we are completed. So that is explaining the failures of VBT. So next here important d orbital splitting. So next concept we are seeing d orbital splitting in octahedral complexes. See, d orbital splitting in octahedral complexes. So the splitting concept is coming from CFT only. So if you see octahedral means what is the hybridization? That is sp3d2. That is the outer orbital complex. Otherwise, D2sp3. That is the inner orbital complex according to VBT. So, what will be the structure? So, metal is surrounded with 6 ligands. So, this is a two-dimensional structure. So actually, so only x and y. So originally in three-dimensional, how do we see? So three-dimensional means you can take a cube. So cubical structure you can take. So middle of the cube, metal is there. Next, in x-axis, two ligands are approaching. So this is x-axis. Next, from y-axis, two ligands are approaching the metal. Next, two more ligands on z-axis. They are approaching the metal. See here. So, in octahedral complexes, so where the ligands are coming? The ligands are coming on the axis. So that means first of all in metal ground state. So ground state d orbital is like this. So now what happens? The ligands are coming close to the metal. Then these 5 are excited. And they are occupying a degenerated level. So they are occupying a degenerated level. Next, where these ligands are approaching the metal on the axis, who are present on the axis, they can feel more repulsion. See, already d orbital we seen. What are that? Dx square minus y square dz square. These are present on the axis. Next, dxy, dyz, dxz. So these are between the axis. See, already these are called as EG orbitals. These are called as T2G orbitals. According to CFT, in last class we discussed. So now ligands are approaching the metal on the axis. Then who are present on the axis? They can feel more repulsion. So repulsion is increases, their energy will be increases. So that's why 2 EG orbitals. So that means dx square minus y square dz square. That EG orbitals are going above from the degenerated level. Next, the remaining T2G. So T2G orbitals, what are that? dxy, dyz, dxz. These 3 are coming down. See, so what you can write in the matter, in the octahedral complexes, the ligands are approaching the metal on the axis. Then the d orbitals which are present on the axis feels more repulsions. So repulsions are increases. Repulsions increases means automatically energy is increases. So that's why the energy of EG orbitals are increases. So in octahedral complexes, the ligands approach the metal on the axis. Who are present on the axis feels more repulsion and their energy will be increases and occupy high energy level from the degenerated level. Next, dxy, dyz, dxz. These are between the axis. They can feel less repulsions from the ligands. So that's why they are occupying lower energy from the degenerated level. So this is the explanation about the octahedral complex. Next, again here we have two are there. Strong field ligand is there. Next, weak field ligand is there. So with that we are going to explain. See, if you want to write the matter means, that also you can write. In what way? In the octahedral complexes. In the octahedral complexes, the ligands approach the metal on the axis. Therefore, the orbitals which are present on the axis feels more repulsions and occupies high energy from degenerated level. So, the orbitals which are present on the axis, who are that? In brackets you can write EG orbitals. So, what are EG orbitals? dx square minus y square and dz square also you can write in the brackets. So, that is. So, this is the explanation of octahedral, how they are going to split. Next, again the important in your NCERT book what they are given. In strong field ligand and weak field ligand, what happens to electronic configuration and CFSE values also they are asking. So now we are discussing entire program. So in octahedral complexes, in the presence of strong field ligands and weak field ligands. See here. First we are taking ground state. So ligands are coming, they are excited. So that is a degenerated level. Next, strong field ligands are there. So EG above, T2G also below. So the gap is very large. So this is what? A strong field ligand. Next, suppose you take weak field ligand. So weak field ligand, what happens? The energy gap is less. So here. This is a weak field ligand. This is ground state, degenerated level. This is also degenerated level. Next, this is what? T2G. This is EG orbitals. So here also, the above is EG orbitals, this below is T2J. So where we are discussing it is in octahedral complexes. Next, suppose here the energy is how much? Plus 0.6 delta 0. So this energy is minus 0.4 delta 0. So total here we are called as octahedral splitting energy. So here also, here to here is delta 0. Octahedral splitting energy from here to here. This is plus 0.6 delta 0. Here to here minus 0.4 delta 0. So already in last class we are discussing that one. So now in what way they are asking d electronic configuration and here also. So one chart we can write d electron configuration. That is one. Next one is a strong field. So one is a strong field classification, another one is a weak field configuration. Here two concepts. One is a configuration. Next CFSE value. Here also it is. One is a configuration, another one is a CFSE value. So already we discussed CFSE value. What is the CFSE value? So number of EG electrons into, so how much? 0.6 delta 0 plus number of electrons in T2G into minus 0.4 delta 0. So already CFSE value also we discussed. So now what happens? Deconfiguration. Deconfiguration means D1 is there, first electron. So how you can write first electron in strong field? So one electron is first here. So in T2G one electron EG is 0. So we can write as T2G1 EG0. Next CFSE value. So T2G, number of T2G into minus 0.4. So that's why it is minus 0.4 delta 0 is the CFSE value. Next you come to weak field. Weak field first electron also fill up here only. So that is also same configuration. T2G1 EG0. Next CFSE value T2G into minus 0.4. So minus 0.4 delta 0. Next second D2. So second electron is also in T2G. Here also second electron is also in T2G. So that's why you can write as T2G2 EG0. So value is 2 into minus 0.4. So minus 0.8 delta 0. Here also say T2G2 EG0 minus 0.8 delta 0. Next D3. So third electron is here only. Here also third electron same. So now T2G3 EG0. So what happens? 3 electrons, 3 into minus 0.4. So minus 1.2 delta 0. Here also T2G3 EG0 minus 1.2 delta 0. See, in strong field, weak field, the one electron, second electron, third electron, everything is the same. Now you come to fourth electron. So here large gap is there. Fourth electron not going to above. So that's why it is combining with here only. So then what happens? D4. D4 in strong field you can write as T2G4 EG0. So 4 into 4 minus 1.6 delta 0. Next, here what happens? The third electron gap is less, so fifth electron is going above. So what will be the configuration? So T2G3, so EG1. So then what happens? 3 into minus 0.4 minus 1.2 plus 0.6. So that means what? Minus 0.6 delta 0. Next, D5. So fifth electron is not going above. Fifth is combining with second electron only. So then what happens? T2G5 EG0 in strong field ligands. So then what? 5 into 4 minus 2.0 delta 0. Next, fifth electron you come here. This is what? Fourth only. Now fifth electron is here only. Then what happens here? T2G3 EG2. So now you see 3 electrons. 3 into minus 0.4 minus 1.2. Next 2 into plus 0.6. So that is also plus 1.2. Cancel. So that's why you are getting 0 delta 0. That. Next D6th. Sixth electron combining with third. You write as T2G6 EG0. So 4 into minus 0.4 minus 2.4 delta 0. Next sixth electron. Now here half field is over. Now it is combining with first electron. So T2G4. You are getting T2G4 EG2. So that means 4 into minus 4. How much? Minus 1.6. Minus 1.6. Next 2 electrons are here. Plus 1.2. So that is what? Minus 0.4. So minus 0.4 delta 0. Next D7. 7 means already 6 are filled. So 7th one is coming to here. So that means T2G6. So EG1. So T2G6 means minus 2.4. So here 1 electron plus 0.6. So that means here minus 1.8 delta 0. Now 7th electron is combining with here. So T2G5. So T2G5 EG2. So 5 into minus 0.4 minus 2.0. So 2 electrons are in EG. So that is a plus 1.2 minus 0.8. So minus 0.8 delta 0. Next D8. So 8th electron is here only. So then what happens? T2G6 EG2. So T2G6 means minus 2.4. Next minus 1.2. Minus 2.4 plus 1.2. So that is 2. Minus 1.2 delta 0. Next 8th electron in weak field. 8th electron is combining here. So this is also T2G6 EG2. So this is also same configuration, minus 1.2 delta 0. Next D9. So 9th electron is combining with here. So what happens? T2G6. So EG3. So T2G6 means minus 2.4 plus 3 into 0.6, 1.8. So that means so 0.6 minus 0.6 minus 0.6 delta 0. Next 9th electron here. So ninth electron combining with this. Here also T2G6 Eg3. So T2G6 Eg3. So here also minus 0.6 delta 0. D10. So 10th electron is combining with this one. So that is you will get T2G6 Eg4. So completely filled. So that means value will be cancelled. You are getting 0 delta 0. Here also 10th electron is combining with 5th electron. So here T2G6 Eg4 you are getting 0 delta 0. So last 3 also same. So first 3, last 3 in strong field, weak field ligand, configuration also same, CFSE value also same. That. So now we are discussing d orbital splitting. In tetrahedral complexes. See, previous we are discussing in octahedral complexes and now tetrahedral. So tetrahedral hybridization is what? sp3. So in sp3, 4 are there. See, in what way? Actually you write in two-dimensional structure. Metal is there, that is surrounded with 4 ligands. So this is a two-dimensional structure. Means upon board or paper you can write like this. But how these ligands are approaching the metal, either on the axis or between the axis, we can't identify in two-dimensional structure. So that's why in three-dimensional you take. So in three-dimensional the best one is you take a cube. In the cubical structure, so metal is present exact middle of the cube. Next, in tetrahedral structure, how you can write means, see, here 2 ligands. Here 1 ligand. Here. So now these 4 ligands are approaching the metal. So this is called as a tetrahedral structure in the 3-dimensional. So this is the 3D structure. If you see where is the axis, this is x-axis. Next, this is y-axis. Next, z-axis is like this. It will go inside. So now by seeing this, these 4 ligands are approaching the metal in between the axis. Next, who are present in between the axis, they feel more repulsion and they will excited to higher energy level. So if you write the matter, in tetrahedral complexes, the ligands approach the metal in between the axis. In between the axis. Therefore, the d orbitals, the d suborbitals which are present in between the axis. So what are that? T2G orbitals. What are T2G? dxy, dyz, dxz. Feels more repulsions. Feels more repulsions with ligands. And they gets higher energy. They gets high energy. from degenerated level and the EG orbitals which are present on the axis dx square minus y square dz square feels lesser repulsions and occupies lower energy state from degenerated level. So this is the matter. So means if ligands are approaching in between the axis, so in between the axis who are there? T2G orbitals are there. So repulsion already we are feeling repulsions. Repulsions are directly proportional to energy. So repulsions, more repulsions happened means their energy will be increased. So now T2G is going above, EG is coming down. It is exactly opposite to the tetrahedral. So now according to this we can write means how we can write. See, this is a ground state. So ground state d orbital. So ligands are coming means all are excited. So that is called as a degenerated level. Next, if ligands are coming very close, so then what happens? So above T2G is going. So dxy, dyz, dxz. Lower side EG is coming. Who are that EG? dx square minus y square dz square. So from the degenerated level T2G is going above, EG is coming down. Suppose that splitting energy, if you are taken, the splitting energy we can taken as delta T, the energy gap between here. So previous we shown delta O. Octahedral is delta O we written. Tetrahedral you can write as delta T. Next one relation is also there between tetrahedral and octahedral. So delta O equal to 9/4 into delta T. So if you know the delta O value, then you can convert into delta T. So how delta T you want means that is 4/9 into delta 0. So previous CFSE values we are identified. That octahedral value you identify and you multiply with 4/9. Then you will get delta T value for these compounds. So in this, who is higher value? So delta O is greater than delta T. So in entrance point of view, this is important. In entrance only. In theory means you can write all those things. See, one more in entrance point of view. So that is a square planar complex is important. So that also we will discuss. That is especially in entrance point of view only. Just you remember that one. So d orbital splitting in square planar. So square planar complex. So it is useful in NEET and JEE. So with continuous manner only, just try to remember that one. Square planar. So hybridization is DSP2. So in 2D and 3D structures, so we can write and we see. See, square planar in two-dimensional structure, in what way? The ligands are like this. So this is a 2D structure. Next, suppose you will see in 3D means you can take as so cubical structure compulsory. So metal is the middle of that. Next, here what ligands are? So 4 ligands only. How to write that square planar means see ligands on x-axis they are approaching. Next 2 ligands are approaching on y-axis. So this is x-axis, it will be y-axis. Next no need to think about z-axis. So z-axis is free without ligands. So z-axis is free. So without ligands. So that's why first of all what happens, these ligands are coming on the axis. So first of all I am taking ground state d orbital. So we are taken ground state. Next, ligands are coming close means these are excited. So they will go to degenerated level. So they went to degenerated level. Next, the ligands are approaching the metal on the axis. Who are present on the axis? EG orbitals. So that's why EG orbitals are going above. So EG and T2G. So who are that EG? dx square minus y square dz square. T2G means dxy, dyz, dxz. See, up to here, this is what octahedral only. So now what happens is Z is absence. Z is absence means the ligands are not there on the z-axis. Every repulsion is feel by x-axis and y-axis only. So that's why x and y feels more repulsion, z feels less repulsion. So again it is further splitted. So what happens? Dx square minus y square is going above. Next, dz square is coming down. Next, here also xy, yz and xz. xy feels more repulsion because of every ligand is present on x and y only. X, y and feels more repulsion. Z is less repulsion. So that's why here xy is also going above. So you are getting dxy. Next, z related they are coming down. dyz, dxz. So this is total splitting energy. So you call it as delta Sp. The splitting energy of a square planar complex we can tell. So compare to up to here. Here to here, up to you can stop means this is octahedral splitting. So here the difference is octahedral to square planar. Z-axis is absence of with ligand. So total repulsion is feels by one is x-axis, another one is y-axis. Whatever related to z-axis, they can feel less repulsions and their energy will be decreases. If you compare all those things, who are more, delta Sp is the highest. Next what? Delta octahedral. Next one what? Delta tetrahedral. So this is also one important in your entrance in NEET and JEE. This is the extra special for extra matter only. So octahedral, tetrahedral is perfectly your based on theory. So how to remember? Just a spot. You can also remember as a spot. Sp is greater than octahedral. Next it is greater than tetrahedral structure. Okay, this is